had been talking a little bit yesterday about the octet rule, that everything wants to have this full outer configuration. Everything wants to have a full S&P because it's stable. And they have low energy that way. They're very stable. There are a few exceptions to the octet rule. We talked briefly about those. Why does this matter? Why do we care? Because they form compounds based on adherence to the octet rule or non-adherence to the octet rule. So what we're going to start to do today is look at how to represent compounds graphically. For those of you who are visual learners, once you get over the hump of doing Lewis structures, you will love it because it's a graphical representation of compounds and polyatomic ions, and especially for those who are visual learners, it makes everything else make so much more sense. If you are going on in chemistry, it is essential. If you're going into pharmacy or any medical field, any chemistry field, any kind of engineering field where you're going to be doing chemistry, visual representation of compounds is critical. When you get into organic chemistry, every single compound you talk about, you represent visually using something that's very much like a Lewis structure. I always thought organic chem notes were the prettiest notes I took in college because they were just all these big, beautiful pictures of molecules doing funny dances on paper. I loved organic. So that's how we're going to use this information. We're going to use this to do Lewis structures. And I don't know if you're aware, on the top of every week on PD Works are your learning goals for the week. And one of the chief learning goals for this week, for this part of this chapter, is represent any compound using a Lewis structure or polyatomic ion. So we're going to be working on that basically for the rest of the week, and we've got a molecular geometry lab to go with that. So you probably did electron dot notation in physical science. All you're doing is showing the valence electrons that an atom has using a series of dots. How many of you remember doing things like this? Oh, there's sodium. It has one valence electron. Yes? Okay. So there are a few things I want to say about this. If you're a rule follower, there are, what is it? All kinds of funny things about rule followers and people who look at the rules and go, oh, I see, that's a nice suggestion. So if you're a rigid rule follower, I'm going to give you some challenges to your worldview. And if you're somebody who looks at rules and goes, well, that's interesting, you're going to be really happy with what comes next. So first of all, you all know how to find how many valence electrons something has. Give me one way to do it that isn't listed on the board. So we can write the noble gas notation and then add up the subscripts outside the noble gas bracket. What's another way to do it? Do what? Well, that'd be a real pain in the tuchus. Then you'd have to figure out which ones were inner shell and outer shell. You could do it. There's a really easy way.
For the S group, it's the block number and the group number and blocks.
Bingo. It's looking at the group they're in, which is what we had started to practice in the last chapter. So S block, it's their number of valence electrons is the same as the group. P block, it's group minus 10. So that's the easy way to do it. You can also, you can do this, and this is going to be consistent down a group. So grab your periodic table, pull that out, one form or another. And we'll actually let's start off with something beautiful. Let's start off with fluorine. It's a lovely halogen, most electronegative element there is. How many valence electrons does fluorine have? 7. It's group 17. 17 minus 10. And if you took physical science and you learned the rules for writing Lewis dot diagrams, that's what these are called, Lewis dot diagrams, you know that you put one valence electron on each side of the atom. 1, 2, 3, until each side has 1. And you very carefully put it on only 1/2. You're imagining sort of a box around this with 2 spaces for each side. And you put 1 electron on each side of the atom until every side has 1. And then and only then can you put a second one on each side until you get up to 7. So what you're left with for fluorine is something that looks like this. And these are very serious rules. And the F, the atomic symbol, represents the nucleus of fluorine. And each of those dots in their location represents a valence electron. And I want to tell you this. There are no little F's stamped on fluorine atoms. You may be shocked to hear this. The little electrons do not line up neatly in boxes on every side of the F, because there is no F. It's a set of symbols that we use to represent something in reality. Okay? So don't get too attached. In physical science, very often you start out doing some very basic, what we're going to move into in more complexity today, Lewis structures, where you're showing how compounds form, especially ionic compounds, let's do a molecular. Let's not. You're showing, how these things could bond, because, well, this one has 1 gap here, and this one has 1 electron. Oh, but then to get that to fit there, we'd have to turn this on its head. And isn't that weird? Well, again, no, because there's really no H stamped on a hydrogen atom. And the electron on hydrogen is not on top of the H because, again, reference my earlier point, there is no H. So it's fine to have rules. If you give me a Lewis dot diagram for something with 4 valence electrons that looks like this, I'm going to call foul. Because electrons do repel one another. So, when you're drawing something, it is a good practice to put those electrons 1 per side until you've got 1 on each side. But don't lose sight of the fact that this is just a symbol set. It's a representation. Okay? There really is no C on carbon. It'd be cool if there was, though it would make it really hard to break that carbon down through nuclear decay and form other things, because we'd have to erase all the C's and stuff. It'd just be a big pain in the tuchus. So, draw for me electron dot diagrams for the following atoms. I'm going to pick 1 out of each group. Lithium, magnesium, well, each of the main groups. Aluminum, silicon, nitrogen, sulfur, and bromine. So go ahead, draw just the straight up old electron dot diagram for each of those. Okay, you should have some things that look like this. Here's where these things are useful, most useful, I think. They're a quick visual clue of how many sites this thing in general has for attachment. So, lithium, if it's going to bond covalently, it's got unoccupied sides. It's, it's got a lot of space to do stuff. If we look at bromine, it's got a full set here, a full pair here, and a full pair here. But what it looks like is that bromine would like to bond with one thing. It would like to get 1 more electron to have that octet to feel really comfortable. It's going to tell us that, sulfur has sort of 2 empty spots. It's going to tell us that nitrogen has 3 empty spots, places where it could share an electron, to feel like it's got 2 on that side. So they're not physical, they're not representations of physical reality, but they're good symbols to help us kind of remember how things go together. Okay? When we get up into the cases like bromine and down to the things like lithium, they're actually less likely to bond covalently. They do, but they very often form ions because they're so far on the ends of the electronegativity spectrum. Okay, now we're going to talk about Lewis structures. So those were Lewis dot diagrams. Those are the really simple, really basic little pictures of individual atoms that, again, give us sort of a clue and a memory tool, a visual representation of how many valence electrons it's got, and an easy, quick way to show sort of how many points it's got for attachment, how many bonds it can form. In a Lewis structure, it's a structural formula, and you're using the atomic symbol to show the nucleus, to show the atom, and you're using dot pairs to show bonds. So if we look at hydrogen bonded to chlorine, I don't think this is one that's on your sheet. We know that hydrogen has 1 valence electron. We know that chlorine has 7. And these two things happen to bond covalently. And we can show that like this. And we see hydrogen, we see chlorine, and we see them sharing a pair of electrons. So the way we usually do this is once we show them sharing a pair, we change that dot pair to just a dash, a line. And the unshared electrons are the only things we really leave as dots. So a couple, if you show this, if you write this and you don't show all of these unshared electrons that chlorine has, what you have is just a simple structural formula. Again, if you're going on in chemistry, you're going to use structural formulas all the time. It's sort of the shorthand that chemists will use for compounds. But for now, we're going to show the unshared pairs. So let's just break down the anatomy of what we've just shown here. We're showing a shared pair or a bond. We're also showing, and I'm going to do this in a different color because I can, these are unshared pairs. They're also called lone pairs, which never made sense to me because they're not alone, they're paired. Yeah?
Could you close your laptop?
Oh gosh, I'm sorry. So those unshared pairs are also called lone pairs. That's another piece of terminology you'll see. There's a guy named Mr. Gooch. I'm not kidding. That's his last name, Gooch. And he teaches chemistry, I don't know where, somewhere. And he has a website called Mr. Gooch's Chemistry. And it's pretty awesome. And as a student, I struggled with Lewis structures. As a teacher, I struggled with how to teach them well. Because by that point, I understood how to do them myself. But I didn't have a good way to explain why I was doing what I was doing. I didn't have a good math-based way. Well, you just know this goes there. That doesn't cut it. What Mr. Gooch developed is a mathematical way to predict how many bonds you will have, how many unshared electron pairs you will have, and really basically the entire structure of your compound. So we're going to practice some stuff. We're going to practice some things. I'm going to try to practice things that aren't in your molecular geometry lab. because I want you to have the joy of doing that all by yourself. So, wait, no, you know what? Let's do ammonia. Let's do boy, it's another thing with, no. Let's do carbon tetrabromide. There we go. So CBr4. It's an organic chemical. It's fairly nasty stuff. We know that this is a molecular compound. We know the formula shows us exactly how many and what kind of atoms are there. So we know this is telling us that this compound has how many carbons? 1. How many bromines? 4. Wunderbar. So if you look at this Gooch math sheet, the very first thing you're going to do is count up how many valence electrons everything comes to the table with. So you're counting up reality, what they bring to the table. Hey, carbon, what do you bring to this marriage? How many valence electrons does carbon have? Look at your periodic table. Fingers, 4. So carbon has 4 valence electrons, and there's only 1 of it. Bromine, how many valence electrons does bromine have? 7. And there are 4 bromines. So 7 times 4 is 28. So how many total valence electrons does this compound come in with? 32. We have 32 valence electrons. If we just add up, so that's our first step. Now, what we want to know is how many electrons everything would have if everything was totally satisfied, if everything had a full octet, or whatever satisfies them. That's why I didn't want to do one with hydrogen first. So our second step, well, carbon would like to have 8, and there's 1 carbon. And bromine would like to have 8, and there are 4 bromines. So that's 32. So if everybody had a full octet, we would have 40 octet electrons. So that's our second step. Now to figure out how many are going to have to be shared, we just look at the difference between these two numbers. So if everybody had a full octet, there'd be 40 electrons, but we only have 32. How many do you guys have to share? Well, we take 40 minus 32. We have 8 electrons that are going to be shared between them. Okay. Now, a shared electron consists, or a bond between a single bond consists of how many shared electrons? 2. So if you have 8 electrons being shared, how many bonds is that? 4 bonds. So your fourth step is getting your number of bonds. And it's 8 shared electrons divided by 2 equals 4 bonds. Now there's one last step, and that is figuring out how many electrons are not being shared. And Mr. Gooch labels this as step 6 because step 5 is actually drawing the darn thing. But we're just going to go ahead and do the math. So if they came in with 32 valence electrons, and they're sharing 8 of those, the rest of them are not shared. So we have 32 valence electrons minus 8 that are shared. How many unshared electrons do we have? I apologize, my cough drops are probably also in the way. And I need them. $26, $24. Thanks. So you have 24 unshared electrons. Well, let's focus on some rules for writing, for drawing Lewis structures. Okay, so we now know, and these are the big important pieces. We know we've got 4 bonds. We know we have 1 carbon, and we know that we have 4 bromine atoms. How do I hook these things together? What goes in the middle? Do I hook them all in a straight line? If you've, the general rule is this. If there's carbon, carbon goes in the middle. I don't know how many of you will get the reference if I go, Marcia, Marcia, Marcia. No? Probably not. Okay, Brady Bunch movie. Marcia's the awesome at everything older sister, and the middle sister would really like to know why she doesn't get any love. Well, carbon is Marcia. Carbon is the center of attention at all times if carbon is there. So if you've got carbon, carbon goes in the middle. So we're going to start off with carbon in the middle. This is where remembering that carbon looks like this is really helpful. Carbon can bond on 4 different sides. And that's pretty fundamental to a lot of organic chemistry if you're going on to organic chemistry. So we know that carbon can actually form 4 bonds off of itself. And I'm going to get rid of those. We know that there happen to be 4 bonds here. So we're going to hook everything together like that. Does that satisfy the number of bonds that the Gooch math said we should have? Yes. Now, what we need to do is draw in any unshared electron pairs. So we're saying that there are 24 unshared electron pairs. And I'm going to actually do that. Nope, I'm going to do that. So I know, and this is where it also is helpful to remember that bromine started off looking like that. Bromine basically has one side on which it can attach to anything. So I'm going to assume that the rest of those unshared pairs around bromine didn't go anyplace. That bromine looks much like it did, except it's now bonded on that one side. That's the Lewis structure for carbon tetrabromide. This is one, and I think in physical science you spend a lot of time sort of turning these things around and lining up little valence electrons on Lewis dot diagrams. But that's really got limited usefulness, especially when we get into things with double and triple bonds, which we'll do more of. And when we get into ions and things like that. So let's walk through another one, and this is one that you'll do on your lab, but we can walk through it together to start with. So everybody's favorite, water. You're full of it. Get it? Never mind. Okay. Because you're full of water, because never mind. Okay, we're all water bags. So to start off with, we want to count up how many valence electrons everything's bringing to the party to start with. So hydrogen, how many does hydrogen have? One. Hydrogen has 1 valence electron, and there are 2 of it. How many valence electrons does oxygen have? 6. And there's only one oxygen. So we have 8 valence electrons coming in. That's our first step. Our second step is to figure out how many electrons there would be if everybody was fully satisfied. And you have to remember something about hydrogen. It's an exception to the octet rule. Hydrogen doesn't want 8 electrons. It can't have 8 electrons. Hydrogen can only handle 2 electrons. So when we're figuring out the octet electrons, this was valence electrons, hydrogen would be happy with 2. There are 2 hydrogens. Oxygen would be happy with how many? Yeah. Oxygen wants 8. So if everybody was fully satisfied, we would have 12, and I like Mr. Gooch's term for it, octet electrons. So the next step is to figure out how many electrons these things are sharing. Step 3, 12 octet electrons minus 8 valence electrons. So they're sharing 4 electrons. How many bonds is that? Just 2. Shrink all this. So they've got 2 bonds. How many unshared electrons are there? We started off with 8 valence electrons. So we'll do this down here as step 6. Unshared or lone pairs. We started off with 8 valence. We're sharing 4. So we have 4 unshared. Now, what goes in the middle? We said carbon, if carbon exists in the compound, there is no carbon here. So the other part of that rule is the more electronegative, the less electronegative element goes in the middle. Okay? So the less electronegative element goes in the middle, or carbon if carbon exists. So we're going to put oxygen in the middle, and we're going to put hydrogen on either end, single bonds. Does that satisfy our number of bonds? How many unshared electrons? How many lone pairs? 2 lone pairs, 4 unshared electrons. Now there's a problem with this. We're drawing something that's 3-dimensional in 2-dimensional space. And those unshared pairs do something. Those unshared pairs actually change the geometry of the molecule. And that's what we're starting to get into when we do this lab. So when you do this lab, you'll not only be doing Lewis structures for everything, you'll actually be building the molecules. So remember how we keep saying water's like Mickey Mouse? We keep drawing it like, whoops, not like that. We keep drawing the oxygen and the hydrogen, and those little ears are up on the top of the head. Why? These unshared pairs actually push the hydrogens away from them, because those hydrogens have a little bit of an electron cloud around them. And those unshared pairs actually force them down. So the way we show this, because it's got those unshared pairs, we don't show water in that shape. What we show is, nope, I can't turn that, okay. What we show is water looking like this. It's a bent molecule. Those hydrogens are on either side. And that's what's shown by the geometry of the model. You can see that the unshared pairs actually push the hydrogens down and away. So basically, when you're bonding something, everything wants to be as far away from other nuclei as possible. These hydrogens don't want to be side by side. They've each got a proton there. Those protons are repelled. But they've also got electron cloud around them, so these unshared pairs don't want to be next to them. So this is one of those situations where everything gets as far away as possible from everything else, and you end up with this bent geometry. So you have to think about how unshared pairs influence geometry, and that's part of what this whole lab will be about. So let's do ammonia. This is NH3. So go ahead and start the Gooch math and then do the Lewis structure, and I'll walk around. So the center is carbon or the less electronegative, or if you've got one of something and three of something else, it's the one, which, is not a technical or official way to put it, but it's the way it works. So if you're still working on this, don't look, but I think pretty much everybody was on track to get that for the structure of ammonia. I would look at least one of these tonight. Tomorrow we're going to go over doing charged structures. So these are all neutral. These are all things that have the same number of protons and electrons. We can do Lewis structures for things that have a charge, for polyatomic ions. So we'll talk about those, then I will hand you your lab packets, and I'm going to turn you loose to work on those. What I will have you do is this, because I'm going to be out Thursday and Friday. I think, did I tell you guys that already? I'm going to be out Thursday and Friday. My mom's having cataract surgery on her other eye, so I get to go off to the hospital and then stick drops in her eye like 43 times a day for the next, I don't know how many days. So what I'll do is, while I'm out, you'll be working on these lab packets. I've included, based on the fact that we have the technology now, I'm going to have you, in addition to doing the paper packet, when you build the structures using these, you will upload a picture of the Lewis structure and this structure, and you'll put that in a document. So what I'll do is I'll have you make those let's see, how are we going to do this? Your lab group will create like a slides document, and you can take pictures and insert them in, and then I'll ask you to do them as you go so that I can pop in and email you or comment if I see a problem, so that you don't entrench bad habits. I think that'll work. So, okay, that's it, and we'll pick this up tomorrow.